Yeah, in the last session, all of you will remember that I have covered what is meant by quality of steel, what is the basic understanding, and I had mentioned it is basically conformance to specified application requirements. Then I had told what are the measures, what are the attributes by which we can measure whether a steel is having good quality or not, whether a component will perform to the desired expectation or not. There I had mentioned for the metallurgical, under the metallurgical quality attributes which are being covered in the particular course. One important requirement is the specified chemistry. That means what are the ranges of alloying elements which have to be maintained for the steel to perform. Then what are the residuals and trace elements? In reality, these have to be kept within limits. That means what are the lower limit of this, or rather the upper limit of these residuals and trace elements. Then I had mentioned about what are the defects, both surface as well as the internal, which should be avoided or which have to be kept within norm. Then I talked about the micro and macro NMIs, non-metallic inclusions. These are called non-metallic because these are not elemental, like iron or sulfur or phosphorus. These are basically sulfides or oxides. So, these are non-metallic inclusions. Then another requirement which I had talked about was the desirable microstructure and properties, because it is quite obvious that the particular steel component or the product has to meet the final properties, the desirable properties for which this is meant for, and for which microstructure is going to play a very important role. What should be the microstructure, whether it is ferrite, what will be the grain size, or whether it is a combination of ferrite and pearlite, or whether it is bainite and martensite, things like that. So, finally, all these will tell you what will be the desirable properties and whether this can be, and all this can result in the final application requirements. I had mentioned also that basically or in principle they can be all these quality attributes, they are generating from two major sources. One, the first I had talked about, they are inherited from the present cast material. Essentially it means that these attributes are evident or present in the parent cast stage itself, which finally will lead to the quality issues in the final product. So, this is very, very important, and in this particular session, as I had mentioned earlier, I am covering only this. That means whatever quality attributes are getting generated from the parent cast stage, these are being covered in the present session. I have also talked about certain quality attributes which are imparted during subsequent processing. That means whether the cast stage has been hot rolled or cold processed, hot forged, things like that. Certain quality attributes might crop up during those processing stages. Those are called processing quality issues, which are not being covered in the present topic. Then I had talked about how these are basically manifested, because we have talked about different attributes, but in the final product in which way these are manifested, these quality issues. First was the surface imperfection. That means that those defects which you can see with normal eye or with some minor modification of the surface, those are called surface or subsurface imperfections. What are those? I have given certain examples, like there may be some surface crack, there may be a lamination, and as if two surfaces are existing side by side, there may be a sliver. Basically it means a very thin line of defect on the surface. So, these are all called surface imperfections, which you do not want to be present on the surface, because this might lead to undesirable performance of the product. Another important imperfection which might crop up, which you cannot see on the surface, basically these are internal defects. That means internal imperfections. those defects we can only see through non-destructive tests. Okay? So, these are basically, we call it internal imperfection. Now, these two broad categories of defects, where from they are originating? It is basically from the poor cleanliness of the steel product. Under that, I had talked about basic thing is the non-metallic inclusions. That means whatever elements, residuals were present in the steel, if they are present beyond a certain limits, they will form some inclusions, which we call non-metallic inclusions, whether oxides, sulfides, oxysulfides, things like that. Now, some of these inclusions might be a metallurgical product of the process of steel making. For example, we know that we have to kill the steel, we have to deoxidize the steel in the processing. So, those inclusions which are formed in this stage, they are called oxides, because basically we are taking care of the dissolved oxygen by using aluminum, silicon, things like that, maybe zirconium, maybe sometimes titanium. So, these oxides, alumina, which are formed during this process, these are called indigenous inclusions, because they are being formed as a part of the metallurgical process. But certain inclusions might be formed because of from some external sources. Those we call exogenous entrapments. I mean, these are all basically or essentially being formed at the stage of steel making, refining and casting process. So, whether it is exogenous entrapment or endogenous inclusions, these are all leading to undesirable surface or internal quality issues. Now, on top of this, there may be some certain poor quality of the casting. When you are casting a particular steel product, depending on the specific chemistry or depending on the specific grade or based on the casting process itself, certain surface, subsurface or internal quality issues might be evolving. For example, there might be some cracks, there might be some surface undulations, or there might be certain defects at the subsurface, or there might be certain internal issues like central segregations and things like that. So, all these are related to the quality of the casting. So, basically there are two broad origin from which these issues are coming. One is basically because of poor cleanliness, which are related to the or originating from the steel making, refining or casting stage itself. And the second one, which is equally important, there are basically presence of certain surface, subsurface or internal cracks or surface undulations, surface defects, which are related to the quality of the casting. That means it is related to the specific grade of the casting or the casting process. I also talked about under cleanliness requirements, we have to look into what are the residual impurities. I had mentioned these are the 5 common residual impurities which we have to be careful about: sulfur, phosphorus, oxygen, nitrogen, hydrogen. Then when sulfur, phosphorus, oxygen, these elements are present beyond certain limits, particularly sulfur and oxygen, what are formed, they are called non-metallic inclusions. Basically they are oxides, sulfides, nitrides or even oxysulfides. Another important cleanliness issue which might crop up in steel and which are also trying to in recent cases they are getting found out in steels are basically presence of trace elements like arsenic, tin, antimony, copper, lead, zinc, tellurium, elements like this, which are elements, metallic elements, but present in traces only. That is why these are called trace elements. These are basically or essentially coming from the scrap which is used for the making of the steel. So, we have to be careful about the source of the scrap from which these are getting incorporated in the steel. I will come to it later on whether to what extent we can take care of this. Now, these non-metallic inclusions, basically their amount, their volume fraction, what are their chemistry, that means what is the type of non-metallic inclusion, whether it is oxide, whether it is sulfide, oxysulfide, what type of oxide is it, their size, their distribution, all these issues are very important and they are going to affect or influence the microstructure and consequently the properties of the steel. So, we have to be very careful. These non-metallic inclusions, if they are present beyond a certain limits I had mentioned, they can affect the surface as well as the internal quality of the steel component. So, we have to be equally careful about those. Now, what I should talk about today is how do you control these residuals. Essentially, today I will talk about very briefly what are the possibilities of controlling the residuals, at what stage of steel making or refining or casting this can be done. So, let us go one by one. We have mentioned that phosphorus is an important residual in steel. So, this can be controlled during primary steel making stages. What are those stages? Either through basic oxygen furnace or electric arc furnace. These are called primary steel making stages because these are the first steel making stage which is used for steel making. So, these are called primary steel making. These primary steel making is essentially an oxidation reaction. We are putting oxygen in steel to take care of the undesirable elements like carbon, silicon, manganese, to control them, because the starting point for steel making is the hot metal or the iron ore, or it may be the scrap where a lot of carbon may be present. So, our first aim is to control the carbon to the limit of steel. So, a lot of oxygen is used at this stage, and here we can take care of phosphorus as well by using basic slag, that means which is rich in calcium oxide. This is called basic because CO is a basic oxide. The ratio of CO and SiO2 is called the basicity of the slag. It has to be at least 2 or 2.5, that means the CO has to be rich in the slag, by which process we can take care of the phosphorus, because phosphorus in presence of oxygen it is forming phosphorus oxide P2O5. This has to be taken care of by CaO, because phosphorus oxide is acidic in nature, CO is basic. So, if you have a lot of CO in steel, basic oxygen furnace steel or electric furnace steel, the CO will take care of the P2O5 and phosphorus level can be brought down in steel to less than 0.25. So, this is very important. Now, let me talk about the dissolved oxygen. In the process of primary steel making, what we are doing? We are putting a lot of oxygen in steel to take care of the other elements. In this process, unfortunately, a lot of oxygen is getting dissolved in steel. But is it desirable? Yeah, okay, for removal of those elements it is okay. We have to use a lot of oxygen during primary steel making stages, but final steel cannot tolerate so much of oxygen. After BOF, the amount of dissolved oxygen in liquid steel is quite high. It may be 500, 600 or 700, 800 ppm. That means you can appreciate it is quite high. Such a big amount of oxygen is of no use in the final steel, because it is liquid steel. When we will be casting it, this oxygen will come out of the steel, will create a lot of pores. That means a lot of porosities will be there. It will be like a strainer, the cast steel. We cannot use the steel strainer because of a lot of holes and pores. So, this high amount of dissolved oxygen has to be brought down after BOF or electric arc furnace stage. This is called deoxidation. This can be brought down to very low level using aluminum, which we call it aluminum killing. Killing basically means deoxidation. If we kill with aluminum, the dissolved oxygen level can be brought down to less than 5 ppm. If we kill with silicon, the dissolved oxygen level is higher, maybe it is around 15 to 20 ppm. But if you want a good quality steel, this dissolved oxygen has to be brought down to less than 5 ppm. So, aluminum killing is a must for sophisticated grades of steel. So, dissolved oxygen can be brought down by, to a large extent, by aluminum killing. Now, all of you will recall I have talked about that sulfur is a important residual in steel and this has to be brought down. How do you bring it down? Not at the primary steel making stage like phosphorus. What we do, sulfur has to be brought down in the pretreatment of hot metal itself. That means it has to be brought down in the hot metal stage itself, in the blast, either in the blast furnace or when you take out hot metal from the blast furnace, before we put it in primary steel making like reactions like BOF or EAF, it has to be brought down at the pre-treatment stage of the hot metal. Or after we have made the steel in BOF EAF, there is a stage called secondary refining, where we are taking care of a lot of refining stages in the ladle, or which is called a ladle metallurgy. So at that stage also we can bring down sulfur. So that means sulfur can be controlled either during pre-treatment of hot metal or during secondary refining. Now let us talk about hydrogen and nitrogen. These are gaseous elements which are present in steel. Now we have to take care of this because these might not be accepted at the particular above a particular quantity in steel in the final product. So we have to take care of this. Now these are done at the stage of degassing, that means at the stage of secondary refining. Now let me talk another issue about these gases, particularly nitrogen. Nitrogen is present along with oxygen in air. Now when we are using very pure oxygen in basic oxygen furnace or electric arc furnace, we are charging air, we are charging rather oxygen. The purity of oxygen is very important. Why you cannot use air here? Because air has a lot of nitrogen. So at that high temperature, when you use, if you use air along with oxygen, a lot of nitrogen also will get dissolved in steel. So the purity of oxygen in BOF or EAF is very important. In BOF we call that oxygen has to be 99.99% pure. Otherwise what will happen, some amount of nitrogen might get into the steel, which is not desirable. So by using pure oxygen, very pure oxygen, we can restrict the amount of nitrogen in steel. Similarly, hydrogen, what is the source of hydrogen? Like some of the raw materials, when they are moist, moisture basically means water. Water has hydrogen and oxygen, and when this moist material is being used in steel making in the form of raw material, as associated with raw materials, some amount of hydrogen might get into the steel. So we have to be careful about not using moist raw materials. And as I have mentioned, this can be brought down to a great extent by degassing stage at the secondary refining. Now another issue is trace elements. I have mentioned that these impurity elements, namely antimony, copper, arsenic, lead, zinc, tin, tellurium, bismuth, these are present only in trace amounts. So these are called trace elements. Now what is the genesis of this element? These are basically coming in steel from the different sources of scrap. Like zinc. When you are using a galvanized steel in the scrap, we might get zinc. Similarly, these elements are coming from different sources of scrap, which we are getting from different sources. We do not know what are the sources of scrap from which all these elements can get entrapped in steel, get incorporated in steel. So these are almost impossible to control during steel making and refining stages. This is very, very important. We should remember that if we are getting these trace elements in steel from the different sources of scrap, these are almost impossible to take care of or control during steel making and refining stages. So what is the way out? Only remedy is careful control of scrap. We should know from where scrap we are procuring, what are the composition of scrap. From the composition of scrap we know whether these elements are present in a large amount or not. If they are present in a large amount, we have to discard those scrap. That means scrap procurement, the source of scrap is very important to take care of these trace elements. You know, this instead of scrap, some amount of scrap is always necessary for making steel, but we can use more amount of iron ore and DRI. These are preferable as input materials to take care of these trace elements, because these sources, iron ore and DRI, they do not have, fortunately they do not have these trace elements, unlike scrap. So if you use more amount of these elements as input materials, the sources of these trace elements are cut off. That means we will get very small amount of these elements in our steel. Now let us see what are the impact of these sources or these issues on the quality. We have mentioned that these are the different parameters which can lead to poor quality. Now how do they impact quality? In which way they affect the quality of a steel product? Let us go one by one. First, let us talk about the residuals. Sulfur and phosphorus, they can cause micro and macro segregation in steel during casting. I will go into the details of this segregation after some time, after certain sessions, but I am just mentioning what are the issues, which can impact quality. So sulfur, phosphorus, their solubility in liquid steel is more compared to solid steel. So when you are casting the steel, these elements from liquid, they will go to the solid state. So the last solid which is going to solidify during casting, they are quite rich in sulfur and phosphorus. So these are the this is the cause of microsegregation in steel, and this microsegregation of these sulfur and phosphorus rich constituents, when they move from one point of one location of the caster or the cast product to the central zone of the cast product, which is the last area which is going to solidify, which we call it central or macro segregation. So this sulfur and phosphorus, we have to be careful, they have to be within limits, otherwise we have mode of micro segregation which will lead to lower amount of solidus. I will discuss this detail later on. Now another problem of sulfur is generates hot shortness. I will try to explain what is it. Possibly you have heard about hot shortness. Now what is it actually? Hot shortness basically means poor toughness at high temperature. When we are reheating the steel product, we want to reheat the steel casting, rather say whatever steel cast we have, maybe we have a ingot, maybe we have a continuous cast slab or bloom or billet, which we are reheating it, taking to a high temperature before hot rolling. So during that stage, if there is lot of sulfur in that particular steel component or steel product, we get poor toughness at high temperature. There may be incipient fusion, because sulfur will react with iron and generate iron sulfide, which has very low melting point, which might melt at that particular temperature of say maybe around 950 or 1000 or 1050. So we have to be careful at what temperature we are going if there is more sulfur. Here the presence of manganese is useful, because if you have more amount of manganese, sulfur will react with manganese and form manganese sulfide, whose melting point is much more than iron sulfide, and we do not have this problem of hot shortness. So manganese is a savior in this case. Now phosphorus and sulfur, another problem, they might cause embrittlement in the normal temperature or even low temperature. So what is embrittlement? That means they make the steel or product, steel component, brittle. That means their toughness is low. There might be crack formation at low temperature. That during some processing we might find crack formation. It may break. So all these elements have to be controlled. Now oxygen, nitrogen, two gaseous element. which may be present at residuals. If they are present in large amount, they can generate pores during casting. So porosity is a problem in casting if you have more of oxygen, nitrogen, hydrogen in steel. So we have to be careful. So what are the impact of the residuals? I have broadly mentioned. All these issues will be taken care of in quite details during the subsequent course of this lecture. Now, what are the impact of trace elements? I have talked about the trace elements like antimony, tin, lead, copper, zinc, arsenic, bismuth. They can cause intergranular segregation. What is meant by intergranular segregation? Most of these elements are surface active, like phosphorus is also surface active. All these elements might go to the grain boundary areas. So they are causing intergranular segregation. By going to the grain boundaries, they are reducing the surface energy. That means the surface energy of the whole product comes down if they move to the grain boundaries. So that causes intergranular segregation. These result in crack and precipitates, because why? All these elements, if they are present in a large amount at the grain boundaries, they might cause crack, they might cause precipitates which are undesirable. Precipitates are rich in these elements like copper or even bismuth or lead. If they are present beyond certain limits, I mean, they might cause cracks or some undesirable constituents. So now let us see what is the impact on quality for non-metallic inclusions. I have talked about the residuals, what are their impacts. I have talked about the trace elements, what are their impacts. Now let me come to the role of non-metallic inclusions. Non-metallic inclusions, I have told you, they are forming if sulfur or oxygen, these are present in large amount in steel. So if they are present in large amount, they will form, or even oxygen, if they are present in large amount in steel, you can get oxides. So this, whenever these sulfides and oxides are forming, we have to be careful of whether we can remove this during the steel making stage. These will be issues. These issues will be taken up in details during the stage of when I take up secondary refining. Now this non-metallic inclusions, if their volume fraction is more than 0.1, if it is 0.2, 0.25, 0.3, we call it a unclean steel. We do not call it like clean steel. Clean steel means this volume fraction has to be less than 0.1. As I have mentioned in the earlier session, that we cannot get absolutely pure steel. Inclusions will always be there in steel. The point is, we will have to control this inclusion, their volume fraction, their size to a desirable limits. Now, when the large volume fraction is present, they will impair the ductility and toughness of the high strength steel. That means the steel will become brittle, and in high strength steel, as such, brittleness is a problem. So we have to be careful about these inclusions. Now, another important issue when you are forming the steel. Suppose we have cast a steel, now we want to hot roll or forge it. Now if you have some inclusions in steel, when you are forming the steel, these non-metallic inclusions are also trying to form. That means they will try to get deformed, like the steel is getting deformed, inclusions will all try to get deformed. So what is important is, what is the compatibility of the formability? That means what are the relative formability between the inclusion and the steel matrix? Please try to understand. Steel, we all know, has a good ductility, a good formability. Particularly at particularly high temperature, we are forming the steel when you are hot rolling the steel. Now, the formability of some of the inclusions may not be that good. Like aluminum oxide. Where from aluminum oxide is coming? As I have told, we have dissolved oxygen in steel. We want to deoxidize the steel. How do we do it? We can do it with silicon, we can do it aluminum. Aluminum deoxidation is good because the dissolved oxygen can be brought down to less than 5 ppm. in the process what is happening? Aluminium oxide Al2,3 is forming in steel. Now these alumina, they have to be slowly taken out of the steel at the stage of secondary refining. That means at the stage of, when they are forming, that means at the stage of deoxidation stage, we have to give enough time for these alumina oxides to float up and get absorbed in the slag. This will be taken up in details later on, but we have to remember at this stage that these aluminum oxides are brittle. When you are forming the steel is getting formed easily, but this alumina oxide, they are not forming easily, so they will be cracking, so there will be interfacial cracks at the interface of this aluminum oxide and the steel matrix. So what we get is a chain of alumina reaction, broken chain of alumina particles in steel matrix, which is undesirable. Now I have talked about the volume fraction, I have talked about this compatibility during formability of steel and the impact of NMI in the compatibility or formability. Now let me come to the use of this term large inclusion. Large inclusion basically means when their dimension, one dimension, whether it is the length or whether it is the width or whatever it is more than 50 micron. It may be as big as 100 micron or even 200 micron. I will come to it later on. The number of such large inclusions will be less, but even if there are a few such large inclusions in an otherwise clean steel, like we may get a situation when the volume fraction of inclusion in steel is less. That means it is less than 0.1. So it is a relatively clean steel, but certain inclusions, very few inclusions, they are large in dimension, maybe 50 micron, maybe 60, maybe 100 micron. Then we may have a problem because they will lead to directionality of the properties. That means certain properties like ductility, toughness. If the longer inclusions are present, not only they will impair the properties as such, ductility and toughness as such, but they will give directionality. That means in the particular direction in which long inclusions are present, their property may be bad. So this is very important, and moreover these long inclusions or long stringers might result in surface defects on the final product. As I was telling you earlier, that we might get some sliver, that means long inclusions on the surface. We might get some cracks because I have told you this compatibility of the formability of inclusion and matrix is very important. Certain inclusions, when they are present, like brittle aluminum oxide, if they are present in large amount, titanium oxide, if they are present in large amount, they are brittle, so they might generate cracks on the surface of the steel, which is undesirable. So I have talked about the different undesirable constituents in steel, like inclusions, like residuals, like trace elements, how they impact the quality of the final product.